Jeff is going to be talking today about industrial flow sheet optimization and estimation using IMPL. And he's going to be talking just generally about how to model and solve industrial types of optimization estimation problems, which require a flow sheet. And these network systems are large scale. There's a number of interesting characteristics with them that he's going to be talking about. You know, it's going to be, I think, a very interesting talk that he gives. Jeff, I'll give a little bit of background on him. He has worked, in advanced planning and scheduling, and advanced process control in the process industries for many years. He has a bachelor's and master's in chemical engineering, and was a research engineer in the APC group in Canada. Which research group was that?
McMaster.
Okay, great. So he's also worked, at Honeywell, and you didn't put some of the companies you've worked for, but I assume most of the major companies that you've worked for, or any of the major companies out there, you've worked for them in terms of planning and scheduling optimization, especially with your work at Honeywell as a consultant. So anyway, with that, I'll go ahead and turn it over to Jeff now.
Thank you for everyone coming, and so for some of the people that I know, appreciate you joining. Go back to the presentation. Okay, do you see that okay?
We can see your screen. It's a little bit slow on the refresh, but we can see.
Okay, I'll go slow. Okay, what I'll do is, John, do you usually allow people to ask questions during the presentation?
Certainly.
Okay, great.
Yeah, keep your chat window open if you can, and for those who have a microphone that isn't working so well, they may put a question there as well. We like to keep this as a discussion, so if there's any points that somebody wants to interject or ask a question, we try to keep that kind of forum for this.
Okay, yeah, and if I don't see the chat window, John, if you can interrupt me and then let me know that someone has asked a question, I appreciate it.
Sure, I'll be glad to.
Okay, so my name is Jeff Kelly, and Alkis Vazakopoulos and I, we've recently started up a small company to do essentially advanced planning and scheduling, but to also integrate data reconciliation, parameter estimation, things like that, in order to be able to take real data and be able to basically update and fit your models better when you do look into the future and do the planning and scheduling. So what I'll do is talk a little bit about the agenda, just in terms of what we're going to talk about. There's about 36 slides, so what I'll do is I'll go through a little bit quickly to make sure that we have some time at the end for questions. So what we'll talk about is a little bit about what industrial algorithms is all about, but very quickly. We have a product called Industrial Modeling and Programming Language, which we'll describe. And then, of course, how do we apply that to industrial flow sheet optimization and estimation problems? And then we'll get into some examples around advanced profit solutions. Really, this is just a nicer way of saying planning and scheduling types of solutions, APS. And then we'll talk about some advanced performance management stuff, which is really advanced production accounting, property tracking, process monitoring. And the reason why we use the word advanced in front, because typically we're using more advanced techniques like statistics, optimization, versus basic stuff that maybe you would see with some other types of applications. So with us, our mission is to essentially develop and deploy important decision-making and data mining types of applications. When I say important, it really means basically applications that have significant benefits, hence the reason why it's important. So what we do is we focus on operating companies, consulting service providers that want to embed IMPL or use IMPL, as well as application software providers in terms of embedding, OEMing these types of the type of algorithms that we have inside of IMPL. As we talked about previously, our focus is definitely the process industry. What we're doing is when you do industrial type problems, whether they're in an offline or online environment, in these types of problems, there's always a flow sheet, meaning there's always a network, there's always a superstructure, there's always material flows from one place to the next, whether they're convergent or divergent. And being able to have a system in place that can manage that type of connectivity is really what we focus on. And IMPL is a language, but what we do is we have these what we call industrial modeling frameworks. They're basically examples, prototypes, things, ways of being able to solve a particular type of problem a lot quicker. So what you would do is we would provide let's say you wanted to do crude oil blend scheduling. So what we would do is provide an IMF for that, and we may have, 5 different tanks and 1 blend header. You can then take that and then incrementally add more tanks, add more crude oils, and it just makes the model development and deployment a lot easier. So what we are is really an enabling technology. Basically, the intent here is to be able to get drive to benefits quicker than if you were to try to do everything yourself, vis-a-vis using something like GAMS or AMPL, some of those types of optimization tools. Basically, you have to code everything, and that can be a huge barrier to being able to ultimately solve large industrial problems and basically get to the benefits for your company. What we do is our focus, or what we consider as a differentiator, is the ability to go after small projects with significant payback, as I mentioned, important ones. A lot of the competition, what we see in industry, is people will buy a huge product, install it, and in a lot of the cases in industry, especially around scheduling, they install huge simulation products, and unfortunately you have to make all the decisions yourself. So what ends up happening, spend a lot of money integrating it, installing it, and in the end, after a couple of years, you realize there's no payback. And that's not really what we're going after. What we're trying to do is basically figure out where you think the bottlenecks or backoffs are. I'll explain a little bit what backoffs are. So that basically you can install these applications. They're typically smaller, they require less overhead, and you can get to benefits quicker. The concept, I think most people know what a bottleneck is, but a backoff, it's something similar, but what it is, it's really, we see this a lot in scheduling. People will reduce their capability artificially just because to make the problem less complex to solve using simulation, they will back off constraints. They'll say, listen, we really can't, we don't know how to make decisions with these kinds of tight active constraints. So they'll back off artificially their capability, and right away you're losing money just because you can't make these more make decisions in such a way that can allow you to push more crude oil through the plant, run to tighter environmental specifications or whatever. So basically, the ability to model more advanced problems quicker is, as you can imagine, an important thing to do. Okay, so in terms of what IMPL is, as I mentioned, it stands for Industrial Modeling and Programming Language. You can also consider it to be Industrial Mathematical Programming Language. Essentially what it does is you can interface your problem, you can interact with your problem, both the problem data, the model data, as well as the solution data. And then what we do is we model it for you in the sense of we generate all of the gingerbread boilerplate types of constraints, material balances, quantity balances, inventory balances, logic balances, logistics balances, as well as quantity times quality. If you have flow times octane, we'll basically generate all of those constraints for you, and what you do is you configure it. And as I mentioned previously, this allows you to basically implement problems quicker. And so our target for that is, as mentioned previously, advanced planning and scheduling, advanced production optimization or process optimization. People would call this real-time optimization, as well as advanced process monitoring types of applications, where we use data reconciliation techniques to solve that. Okay. So how do we basically what we're trying to do here is to allow you to configure the models as opposed to coding. Coding in some cases can be a negative, but in other ways, a lot of times coding in the context that we have here is really how do you integrate it to your data systems. So what we have is we have a flat file interface we call industrial modeling language. I'll show you a little example of that. And then as well, we also, all of the ways to configure the problem using the flat file, we also have the same APIs essentially that you can do that with inside any programming language, such as C, C++, C#, Java, Python, and then a big one, of course, is Excel VBA. So everything that you can do with IML in a file, you can do as well in a programming language. How basically you define, if you were to use GAMS or AMPL or something, you have to work with what are called sets. So what we have inside of IMPL, instead of using sets, well, these are kind of like sets. We call them more shapes or objects. So everything in our case is keyed using Unit-Operation-Port-State Superstructure. It allows you to define units and operate, and these units can have one or more operations. Ports allow you to put material in and put material out. State is a carryover if you're familiar with batch processing stuff. State task network or resource task network. We include the state label or object. And then, of course, what we do is, so that really defines the structural aspects of the problem. Then we allow you to configure what we call phenomenological variables. These are quantity, logic, and quality types of variables. And as well, we manage time for you, because essentially, when you're doing planning and scheduling problems, these are all have basically a time index to them, because in a lot of cases where we need to look into the future 1 week, 1 year, and we break it up into multiple time periods of 1 hour, 1 week, what have you. You know how it goes. So we also manage time. An example of the IML, we call these frames. These are basically like sheets that you would have in Excel. So you can generate these frames from Excel. And so what you would do is, if you have the first one here, it says unit operation, uptiming lower and uptiming upper. This is an example of us configuring runtime, minimum, maximum runtime constraints, or we call them uptiming constraints. And so if you have a blender, and this blender can blend some crude oil, and then you have a lower uptime of, let's say, 3 hours, then instead of having to go in and go to the literature and figure out, gosh, how do I code up minimum run lengths, you basically here you would configure it. And this is how you key it using Blender, unit operation, or unit operation port state. So you can have uptimes on basically flows between one unit operation port state to another unit operation port state, and so on. So this is how you basically configure the problem up, where instead of using your own types of sets where you have to manage all of your compound sets and subsets and index sets, we do all of that for you, as well as we'll actually create all the constraints for you as part of what I was calling previously modeling, or the model. You can do the same thing, and this is an example using Python, using IPL, Industrial Programming Language. And the way to do that, there's a interface module inside of Python called ctypes. So you can take our DLLs and you can populate, as I mentioned, any aspect of the problem that you can do within IML. And this basically would encode the model inside a programming language. It has some good and bad points in terms of maintaining the models. But you know, it's a nice way to do something online. You can create the model completely in code, as well as it's an easier way to get the data out instead of having to parse flat files. You can extract the data from our database very easily. We have what we call 6 system architecture parts or components. We're trying to keep the system architecture very, very light, simple, small footprint. So as mentioned, we have a server which essentially manages the all of the data in terms of the basically the variables, the constraints, the parameters, the coefficients, all that kind of stuff. We have the interfacer, which is really the IML, the interactor, again, which is the IPL. We have a modeler, which, as I mentioned, this is what would generate the constraints, variables, and constraints for you. Then we have a pre-solver. This does more than pre-solving. This pre-solves the problem, tries to reduce the problem as much as possible using essentially LP pre-solving techniques. And then it also is the interface to all of the solvers that we support that I'll list out a little bit later. In terms of how we, previously described how do we model the problems, how do we solve these types of large industrial problems, and invariably or ubiquitously in these types of problems, we always have quantity, logic, and quality, which really are a mix of continuous and discrete variables, so we always have MINLP problems to solve. What we do is we do not solve an MINLP. We don't believe there's any solvers out there that will work for industrial size problems. What we do is we essentially break it up into 2, and what we're calling now with Breno Menendez, who's on the call, and he's doing a PhD partly at Carnegie Mellon and at the Technical University in Rio, is a phenomenological decomposition where we're putting a little bit more science to how we're integrating these 2 types of subproblems. But essentially what you can do, you can set up a logistics problem first where you proxy the nonlinearities using what we call yields, or these are called conjunction values. So you'll solve an MILP, you'll then fix the binary variables, and then you will go and solve a NLP. And what you do is you iterate around there until you get solutions that you feel that you can implement, that they make sense. And essentially what we're doing here is we're going for not global optimality. In fact, that's the next step above MINLP, which makes the problems even harder to solve. What we're really going for is global feasibility, because really that's really business as usual. When people in industry, you know, you can talk about optimality, you can talk about optimizing, which we're trying to do, basically doing improvement. But really, when each of the process units, for example, each of the sub-businesses, if everyone's feasible, that's business as usual, and that's what we're trying to go for, is finding solutions to these difficult, continuous, and discrete problems, but in intuitive and practical ways. So this is what we would call a primal heuristic. It's really like a truncated Bender's decomposition, but it's extremely effective in industry. It's nothing that we developed in terms of the concept. I can point to many people in the past who've done something similar. So essentially, it's a natural way of decomposing the problem, and as I mentioned, trying to get global feasible solutions out. Between each cut, between each solution of the NLP and the MILP, to cut off infeasible regions or parts of the model space, search space that you don't want. One technique you can do is to add extra constraints, or in mathematical programming terminology, we call these cuts. So you can do stuff like that. That would be basically extending conjunction values with conjunction constraints, so to speak. Okay. In terms of the types of solvers that we support, basically we support all of the NLP stuff like CONOPT, IPOPT, KNITRO. We had a discussion previously. This is how I met Alkis. Honeywell started with Dash XPRESS SLT, which there really wasn't, in 2001, there was not a commercial SLT out there. A lot of homegrown stuff with PIMS, RPMS, GRT MPS, to do essentially oil refinery planning with distributed recursion, a little bit of SLP, but nothing in a real rigorous way. So the FICO has a solver called XPRESS SLP. It's very good. We also have our own SLP, but we also will include a QP if there's some quadratic objective function terms, which is very typical you find in data rec and nonlinear control problems. So these are the types of solvers we have. We have our own SLP QPE, which can call any of these LP or MILP solvers, whether they're commercial or they're open source. So the big one that really started it all was CPLEX. There's XPRESS, GUROBI now, as well as some of the open source stuff like LPSOLVE and SCIP and COINMP. So essentially, if any solver that uses a matrix, then it's not a problem to interface that. Okay, so the previous stuff was basically talking about what IMPL is. Now, the next part of this presentation is to describe what is industrial flow sheet optimization and estimation. And we've listed 5 requirements to do that, or essentially 5 things that you need to be able to implement industrial flow sheet optimization and estimation. The very first one you need is an unambiguous representation of the flow sheet network or superstructure. We use this thing called Unit-Operation-Port-State. It's more than just a network, it's a superstructure in the sense that units can have operations. For example, if you have a crude unit, you're going to plan that. Typically, a crude unit can have 3 different operating modes. One can be fuels, the second one could be lubricants, and the third one could be asphalt. And I used to work for Shell Canada in Imperial Oil in Canada, and at Shell Canada, they would have what was called a boomer run, blocked out Montreal East Refinery asphalt run. And so managing modes on units is a very important thing. So having a network structure that can do that can manage both batch processes, which is really what the state test network is, started by Kostas Pandelides in Imperial College. We've extended that to not only handle batch processes, but also continuous processes. So IMPL can be used for batch process industry or continuous process industry because we have a unique way of managing essentially the complexity of these types of problems. The second thing you need, we've taken this name from John Hooker at Carnegie Mellon. We basically talk about the quantity, logic, and quality phenomenon as semantic variables and meta constraints. Essentially, you don't just define a continuous variable X and a discrete variable Y. In industry and in any application of an optimization problem, there's semantic. The variables have a meaning. In our case, we have quantity variables, logic variables, and quality variables, and they all have a meaning. And meta constraints are simply the notion of having one type of constraint that will generate many more constraints. So it's basically constraints of constraints. And that's also what we do inside of IMPL. So we would consider IMPL to be an instance of the theoretical concepts from John Hooker regarding semantic variables and meta constraints. The third thing you need is a way to manage time. And essentially what we do, all of the data, all of the temporal data, everything that you put in to IMPL is all put in continuous time, and then we have a digitization engine that will discretize it or distribute it across different time periods. I won't get into all of the hot topics, hot conversations around continuous time scheduling and things like that. But this is to do industrial flow sheet optimization and estimation because we can have dynamic models and looking into the future and things like that. You always need a way to manage time with it. The fourth thing is optimization and estimation, and if you have simulation, I know this is what John's software does, APM. It has a nice way of managing optimization, estimation, and simulation. If you take the Fortran 2003 term interoperability, essentially this is what we need with these tools as well. The first time I ever got exposed to this was when I worked at Shell using Opera, which Jeff Renfro was one of the inventors of that, who's on the call. Basically, you could solve a data rec problem first, and then you take the solution of that, and then you solve the economic optimization problem. This is essentially how RTO works. So the idea of optimization and estimation interoperability is absolutely not new. But if you're going to implement an industrial modeling system, solving system, you definitely need these kinds of concepts and be able to handle the fact that you know, I want to solve an estimation problem, I want to fit, I want to tune my plant, and then I want to take the same data or different data, same model, and then look into the future. We're calling that interoperability. The fifth thing, of course, is just looking at your data. When you bring the data in, instead of doing a pre-solving, you really want to do a pre-screening of the data. And so we have certain techniques inside of IMPL to allow you to do that. I won't go into much detail about that, but data, of course, data quality, of course, is a big deal when you want to solve these industrial types of problems. Okay, so this is how we represent the different types of shapes or objects with respect to this unit operation port state stuff. I won't go through it in too much detail, but what we do is you have these different types of shapes that in our case, you can use the open source genome DIA. It's very similar to Microsoft Visio, and you can drag and drop these objects, and you can essentially configure up your superstructure network. You can read about some of this literature. If anybody wants any of the literature that I've put inside the references, please let me know and I can send them to you. So essentially what we have are perimeter units. These define the boundaries of the problem. We have pools, which are inventory. They're tanks, spheres, caverns. As I mentioned, we do batch processes, continuous processes, and then continuous processes, we break it up into different subtypes like blenders and splitters and fractionators, reactors, and black boxes. Basically, you can create your own type of unit. Dimensional processes, these are good for pulp and paper or metal casting. You take bulk liquid, bulk aluminum, put it and convert it into an ingot. It's an idea of a dimensional process. The upside down triangle is movable inventory. It's like a ship, it's a barge, it's a truck, it's a rail car. We do pipelines. We manage the first in, first out. And then in a book chapter a few years ago, Danielle Zinger and I, we added, which no one, believe it or not, ever done before, we modeled using MILT. Not FIFO, first in, first out, but we did LIFO, and this has a big applicability in mining when you blast the side of a mountain and you start stacking the ore. The last truckload you put into a pile is the first truckload you take out. So managing that as LIFO is very important. And then, of course, to make the flow sheet unambiguous, we have these things called ports, imports and outports. Okay, so in terms of how do we formulate the variables and constraints, as I mentioned, we have these quantity, logic, and quality variables. What we do is when we combine quantity and logic together, we call it logistics. And when we combine quantity and quality together, well, not that creative. We needed a Q word here, so we'll just call it a quality subproblem. Examples of different types of semantic variables. We have flows, holdups, and yields for quantity variables. Logic variables, in chemical engineering, you really don't learn too much of this, but in order to solve scheduling problems, you really need to define setup variables, startup variables, switchover variables, shutdown variables, and to do sequence-dependent switchovers, you need some other variables to manage that. So this is sort of like I have a hydrocarbon processing paper where I'll call this essentially the missing link to be able to do real types of blend optimization. You really need to understand the logistics of or the logic of the problem. Quality details, chemical engineering, we know that quite well. Densities, components, properties, conditions. Conditions are like temperatures and pressures. And then also we've added coefficients. These are like parameters that you can fit. So you can fit catalyst activity, or if you don't want to fit it, or if you have some empirical correlation where you can use some, what are they called, phase equilibrium, equations of state, sorry. You can actually call out to a DLL that has those third-party property packages, and you can load them into IMPL as coefficients. Okay, so as I mentioned, we do have managing time is always so important. When you put in data inside of IMPL, you give it as orders or transactions, which means you say how you may have an order of crude oil coming in, so you have to tell it the type of crude oil, you have to tell it how much crude oil is coming in, then of course you need to tell us when is it going to arrive at start time, and when is it going to stop being transferred, its end time. You put all of that data in as a order, and then internally inside of IMPL, we then digitize it, but we'll either do discrete time, or we'll do what we call distributed time. Distributed time is like discrete time, except we have unequally spaced time points or time periods. Very good for NLP if you don't want to have a lot of time periods when you're solving like what some people would call stiff problems. We're working on some ways of using distributed time for logistics types of problems, but then that gets into the discussion around continuous time scheduling, which we won't get into. But just remember the fact that when you do these industrial problems, time is really important. Okay, so how do we manage interoperability? Essentially, nothing new here. Same model, but just different data. In the optimization that we do, or you can say really kind of any kind of industrial optimization, really it works off of future data. You're always looking into the future. Even if you're doing real-time control optimization, you're still looking out 90 minutes, breaking it up into 1 minute time periods. So you always have that future data aspect to it. And then estimation, you could argue, is really you want measurement feedback. Of course, you can only have it in the past and present. You can't have measurements in the future. So what we do is we manage the future data and the past present data for you. Ultimately, the goal here is to be able to calibrate, adapt, fit, tune, these whole bunch of different words to say that you want to basically do parameter estimation on the past data so that you can improve your model. And that's very, very similar to what's happening now with moving horizon estimation. So this is really just an application of that. Mentioned quality of data. It's like pre-solving in LPs. We're calling it pre-screening, but you can do things like do check for unsteady state behavior. This is how I know John, we have a little paper that we think we have a better little algorithm to do steady state detection. So, it's nice to know, is your plant steady? If it's steady, then, apply some optimization to it. Or if your plant is just plain too many intervals of unsteady, you may have a problem with your advanced control. So that's a problem in itself. So, and the other thing to do is we have a whole bunch of data reconciliation technology in here too. So doing little simple conservation laws, checking for gross errors is always a good thing to do. Okay, I'll speed it up. So what we do here is we have lots of stuff as mentioned, around planning and scheduling, advanced profit solutions. The reason for saying that is because inside the objective function, especially planning and scheduling, you always have economics. We're always trying to maximize revenues, minimize costs, what have you. So it's planning and scheduling. You really start to look at the economics. Some people could call it profit, and hence the term. And that's no different with what we do. Some examples of that are this, real quick. As I mentioned, this is we've drawn this little flow sheet superstructure inside of Genome Dia, and this would configure the flow sheet. And so you can see these perimeter units, which are the diamonds, the ports, the outports, which have an X on it, the triangles, which are inventory. Continuous process here, which is really a crude unit, or some people call it a pipe still. And you have different cuts. So being able to manage the network, the flow sheet, in a convenient way is what we do, as well as managing, I put some key logistics details. So you can have things such as, a nice one here is, when you fill a tank, you can have what we call a fill draw delay. Essentially what it means is, when you put material into a tank, you cannot take material out. In this case, you would configure 9 hours. So you cannot take material out until after 9 hours. That you see that a lot when you have crude oil deliveries from the ocean or from marine deliveries, where there's lots of ballast water. So you need to put the crude oil into the tank, and then you need to let it settle for a certain amount of time. 9 hours is probably a little too short. It's more like 24 hours. And then you would then remove the water. Then you could send it to the desalter and the downstream crude unit, and then you'll have no fear of blowing out the trays in a crude unit. So managing logic details in an automated way in terms of understanding the temporal capability or capacity of problem is extremely important. But we don't really talk about it in those kind of terms, but this is what we're trying to do with IMPL. Here's an example of the Gantt chart. There was a setting that said that the blender uptime should be between have a minimum of 3 hours, and you can see that it's hard to show the individual 3 hours, but just take my word for it that the run length has been respected. There's also a run length for the flows of the crude oil that come from the charging tanks into the pipe still or crude unit, and that's why you see this. In this case, it was 19 hours. That's why you see a nice long flow out of a tank. It doesn't. You can just flow in as fast as possible, but you see these nice stretches of flows out because you want to make sure that you can maximize the flow out of a tank going into the crude unit, because that can then define a nice crude run. So you have at least 19 hours where the quality of the material going into the crude unit doesn't change. So you can start to hone in with your advanced controls and start making great product. And then of course you have problems when you switch over between different tanks, but that's another story. Okay. We can do the same thing with product blending. Same idea. As I mentioned, I have this paper in hydrocarbon processing where I talk a lot about the logistics details for that, so you can email me and I can send that to you. I won't go into too much detail around this. In terms of managing some details around how do you specify nonlinear problems into IMPL. So for example, you can, here's an example of creating evaporation, which is very important to do distillation blending. In fact, Breno and I are going to be having a paper on this. So what we're doing here is you can basically configure up a monotonic spline. That's what the SCIP means. You give it the different data, the data set or list of data, breakpoints, if you will. And then in our case, both the X and Y axis can also be variables. So we have a certain techniques inside of IMPL to make sure that, you know, when you do interpolation or linear interpolation or spline interpolation, for example, that your X values must be in ascending order. So we have a certain technique that can manage that by ranking the different variables. So, you know, there's a lot of people when they start hearing interpolation inside of optimization and start getting scared, but it's a very important thing to do, especially in this case to manage distillation, temperature distillation stuff. But there are nice things you can do, especially when you're using equality nonlinear programming to help, essentially smooth out and manage some of those discontinuities, not perfectly, but in a good way. As I mentioned, you can create a coefficient. In this case, you can call out to the STEAM 6060LL, and you can bring in enthalpies. You can also easily model ASTM D86 to true boiling point as ad hoc equations inside of IMPL, and then you can create your own external functions in IMPL that will be used inside the compiler. And so you can basically extend IMPL to do any sort of nonlinearity that you want. And then some of that stuff we talk about, Danielle and I, we're not sure when this book chapter is going to happen, but there's a book chapter on optimization analytics in the oil and gas industries. So we talked about a lot of these details there. A recent thing that we're doing with IMPL, which we don't believe anybody else has ever looked at before. Again, there's always a network, there's always a flow sheet. So what we're doing is that in a lot of chemical engineering stuff, people looking at process design synthesis, some of the stuff around capital investment planning, looking at retrofits, there would be specialized formulations for that. But when you look at it from a semantic or meta constraint perspective, you can view this in a different way. So retrofit fit problem really looks like having your existing plant. Here's like a little example of a Gantt chart. Here you have an existing plant, and then when you want to move from the existing plant to the extended or expanded plant, basically you've spent some money, you've put some construction into it, and you basically either want to increase its capacity or increase its conversion. You can think of there's a commissioning phase that you would put in between. Well, in fact, that turns out to be no different than doing sequence-dependent setups, where you're doing repetitive maintenance, whether it's a cleaning or a purging type of operation. So when you take the process flow sheet in terms of the products and different operations that your plant would have, when you add sequence-dependent switchovers, technology, and then of course there's Danielle and I have a paper where we talk about the real details of doing what we think is a smarter job of formulating sequence-dependent switchover problems. When you put those two together, you can solve the retrofit problem, but when you think about it even a more holistic perspective, you can also use the same technology to solve the repair problem or the maintenance planning, turnaround, and inspection, where people basically put in Excel a bunch of scenarios. Should I shut down the cat cracker first or the crude unit second? How do I manage inventory? Well, if you already have a way of managing the production, and then you add the sequence dependent, then you can start automating decision making around turnaround scheduling. So this is something that we're pushing to the industry, and then Alkis, myself, Breno, and Professor Grossman, we're having a little poster at the Informs, the next Informs meeting, where we're discussing that in more detail. Okay, I'll go through the other side, this what we're calling advanced performance management. Essentially what we're doing is use the same type of model that you can use past data and essentially do nonlinear data reconciliation. Before I got into planning and scheduling, I was doing a lot of data rec things, and so being able to do advanced production accounting, meaning advanced meaning you're using statistics, advanced property tracking, advanced process monitoring, very important things to do, but the most important part about it is being able to provide diagnostic information. And of course, the diagnostic information that we're talking about is really given a flow sheet, solve it in such a way that you can determine the redundancy of the measurements, the observability of the unmeasured parameters, put a whole counting statistic around the overall sum of squares objective function, very good thing to do, and then have individual maximum power statistics that you can detect gross errors in the system by minimizing type 1, type 2, type of errors, false positives, false negatives, and doing all of that in an automated way around your flow sheet. You know, not new, but surprisingly, not a lot of people are doing it properly. So it's always a good thing to do, but there needs to be an easier way to build your models to do it, and that's what we're trying to do with IMPL. How we do it, we can do both unconstrained data rec or using, you know, these basically LU decomposition solvers, or we can do constrained data rec. You can use IPOPT, CONOPT, anything you can solve an SQP. We can do. So you can put bounds on it. And then, of course, you want to get all of that sensitivity information. So the academic literature approach is to use things like reduced row echelon form, Guest-Gordon, QR factorization, SVD. We don't use those. We have a sparse technique that can solve flow sheet that basically do the compute the variances and the observability and redundancy in a very, very fast manner, because you can imagine these flow sheets can be quite big. So doing it in a sparse matrix framework is a really good thing to do. So that's how we solve it. So it's kind of unique in terms of how we do that, but it gives you those important metrics. These were just some examples of, again, the commonality here. Of course, you'll see all the examples have a flow sheet to them, and that's basically the thesis of the talk. I won't go into it in too much detail. But you can certainly do dynamic problems in IMPL. So you can time lag variables. So essentially what we're doing here, we're taking the pretty popular nonlinear problem and from this nonlinear process control book, and we're essentially doing Euler's integration and basically solving for in this case, we're solving for I think the coefficient here we're looking for is the UA heat exchanger term. And we have IMPL embedded in a civil engineering material flow analysis product called STAN, and you can download this for free, and you can use IMPL inside of there. So that's just an example of using where it's, you know, so this is an example of an OEM'd or a embedded product. I won't go into too much of the benefits. In terms of this is my last slide. So in terms of taking the benefits of doing APM integrated with APS, of course there has to be a reason for doing that. And 2008, Danielle and I, we presented at the FOCAPO a small example where we show that when you do planning and scheduling, and if you do not do what we're calling parameter feedback, which is nothing more than just fitting parameters to the model, then you will always encounter significant and persistent offsets between plan and actual. And then, you know, when you have these monthly meetings, you look at what you planned, you look at what actually happened, and you think, oh my God, it's a problem. The problem isn't with the plan. The problem, of course, is with the people who executed it. Well, in fact, no, not so fast. Your plan is probably wrong because you're not adapting your models to the way that the plan actually runs. So, in fact, I mean, there's always execution problems and always scheduling problems and always uncertainty. Don't get me wrong. But this notion that the plan is always right is not correct. And this is just basically applying simple advanced control techniques and just looking at the fact that you're going to have steady state offsets when you do not have, again, what we're calling parameter feedback, which is nothing more than just implementing moving horizon estimation. So this is just a small example to show that it is important to have both techniques when you're doing optimization. Okay, so that's it. Thank you very much. Hopefully there's some time left.
Yes, there is just a little bit of time left for questions. So, and thank you, Jeff. I thought it was a very good talk on, not only some of the techniques that you're developing and applying, but applying those to very relevant, large-scale industrial applications. So I thought very informative and very good talk. So let me go ahead and open it up for questions now. And let's see, go ahead and unmute your microphone if there aren't, so you can interject, or let me let everybody unmute as long as you don't have a lot of background noise. And then we'll just go ahead and enter the question phase. So go ahead and ask a question if you like.
Okay, well, I've just put a question in the chat.
Okay, so I'll go ahead and read that. I'm impressed by how powerful your platform is. What language is it written in, and how many lines of code?
I'm not going to tell you the language, but it's written in the oldest and newest language known today.
I'm guessing that's probably Fortran.
Yeah, it is.
Okay.
Yeah.
Great.
Yeah. Yes.
That's
it's Fortran 2008, and so one of the things that one of the extremely powerful things about Fortran, of course, is not, especially Fortran 2003, is not only its interoperability, and that's where I'm using that term, between Fortran and C. So basically, no one's going to write. Well, not so many people write LP codes now in Fortran. They're always, typically written in C, maybe C++. But for us to integrate Fortran to C is seamless. So Fortran's really great for that. But the other big reason why we're using Fortran, but of course you could do this in C, is the complex algebra. So when we do all of the derivatives, so when you put in all of your ad hoc models, so you can write any equation inside of IMPL you want, and you do not have to provide us with any derivatives. We use the technique called complex step derivative method. I'm not sure if you ever heard of it. Basically, you perturb the imaginary part of the variable, you take the imaginary part of the constraint, divide by the perturbation, and you get basically numerical derivatives of analytical quality. And so Fortran has the best complex algebra to do that, and hence Fortran works out well. Okay, next question.
Okay, great. Okay, any other questions?
Chef, this is Bruno Calso here. I have a quick question for you. Okay, I was just curious about because you talked a little bit about the splines and interpolating stuff like in NLP. So I was just wondering if you could say a little bit more about how do you go about integrating these interpolation models into an NLP, because are you using derivative information? And that also goes to the pieces of equipment in the flow sheet. Are you using like an equation-oriented way of to have all the equations out there, and so you can do the derivatives exactly, thermodynamic packages, and all these things are in the same question that I'm trying to ask. If you got it.
Yeah, okay, yeah. So basically, if I just focus on the spline, okay. So we have, in this case, we have two types of splines. One is the Hermite, piecewise Hermite spline, which was basically you could download some Fortran code. Now, what we did was we complexified it. We changed all of the real star variables into complex variables and done some little tricks to do the binary search. But so basically, when you evaluate the functions, when you call it again to evaluate the derivatives by perturbing the imaginary part, if any ad hoc function is been properly complexified, then you will get the derivatives for free. Well, no, sorry, not for free. I mean, just you still have to do the computation. So when you supply the models inside, we do the automatic first derivative. So I'm not sure if I answer your question. Now, if you're to think about, so here's one complaint with the current physical property packages that are out there, for example. So if you notice here, Steam 67. So we downloaded some piece of code, arbitrary code, from Steam 67.dll, which does, basically water is a pure component and does all the physical properties. Now everything was coded in that in RealStar 8. So we have to add some perturbation stuff to compute. So in this case, the derivatives are not as good as complex step. But if you had the source code for these property packages, and you were to recast the variables as from real star 8 to complex star 8, then getting high quality derivatives from these physical property packages would be relatively easy. But right now it's really difficult to and Jeff Renfro is probably the guru of this, to get high quality physical properties to put inside of optimization. But if you were to take the complex step approach, we could get much better derivative information from physical property packages if we were to basically recode them in an easy way. So again, I'm not sure if I answered that question, but it was just more of a plug for complex step derivative method.
No, yeah, you did. Thank you very much.
Okay.
Okay, maybe time for just one more quick question. Okay, well, I think that's we're about out of time.